So we're almost there. Yeah, this question. Yeah, but the last thing, we need to write the y function in an explicit form, not implicit form. Implicit form not very convenient to use. So we want to have an explicit form, very easy to use. Yeah. All right. But the first thing is, if you look at this, our newest representation, the natural log, inside natural log, there is an absolute value. We know when some expression contains absolute value, it's not very convenient to use because you need to consider cases, right? Greater than 0, less than 0, not convenient. If we can get rid of absolute value, then we do not need to consider the cases, right? Yeah, so usually, so we want to use the existing information to help us get rid of the absolute value. All right. Inside the natural log, absolute value of 5,000 minus y. 5,000. Okay? Yeah. Minus y. Yeah. First, the y amount of salt, right? Amount of salt in a tank. Amount of salt in a tank. Yeah. All right. So here, amount of salt in a tank. Is it possible that amount could be greater than 5,000? Is it possible? No, right? Yeah, because the initial amount is 100 pounds, right? Initial amount is 100 pounds. Okay? All right. So then, so every time you 5 pounds per minute, 10 gallon, so 50 pounds per minute. Yeah, let me see. Yeah, is it possible to, think about, is it possible to be greater than 5,000? Yeah. Yeah, because, so here the question. Right. Yeah, so think about that. Is it possible? We need to make some good argument. Yeah. Here. Yeah. Remember our 4 steps. Our 4 steps. Step 3, after we find a solution. Step 4, we need to do some interpretation. Right? Interpretation. Yeah. So we need to go back to the original question and use the given information. We do some further analysis. Now, here, we need to do that. Okay? All right. So the one question is it possible that y amount could be greater than 5,000? Yeah. Because we need that information. Yeah. When we try to remove the absolute value, we need that information. Yeah. All right. So here, yeah. Our guess, our guess is it cannot. Why cannot? Yeah, but that's the guess. You need to you need to convince people it's correct. Okay, so you need to find solid information to back your argument. Okay, yeah, all right. So here, let me leave that to you. Okay, yeah. So it's an interesting question. Leave that to you. Okay, think about it. Yeah. So if our claim, so here we claim y can never be greater than 5,000. Okay, or we claim y is always less than 5,000. Okay, yeah. But we need to, prove it. Yeah. Our claim is correct. So you need to use the existing data to prove it. Okay, all right. So here, I leave it to you. So next time, let's try to answer that question. All right. So here, if our claim is proved, we can write that equation, without that absolute value. All right? Yeah. So here after that, we remove the absolute value. 5,000 minus y function equals e to the c. That c undetermined. We need to use the initial condition to determine that c. Yeah. So then another e term. Okay? Yeah. All right. This time we need to plug in when t equals 0. When t equals 0, let's plug in, okay, to find that e to the c term. All right. So when we plug in, yeah, so we can get e to the c equals 4,900. So we can replace e to the c by that constant, 4,900, that constant. Okay? All right? Yeah. So next, yeah, so here, yeah, I write the function. Yeah, so let me erase. Yeah, so I just put here. Yeah. The final expression of the function, y function, equals, this is explicit form, 5,000 minus 4,900 times e to the negative 0.01 t. Yeah. The solution. Yeah. So we find the solution. We find the user-friendly solution, explicit form, easy to use. Yeah. Okay. Yeah. Yeah. But I leave that question. So you need to, convince people. Yeah. Why we can remove that absolute value. Okay. Yeah. Because later we will have many questions. We need to remove absolute value sign. Okay. Yeah. We have so many questions. We need to remove absolute value. So here I give you as our first practice. Yeah. Because when you remove, you need to make a good argument. Yeah. Do some simple analysis work to convince people. So you have some good reason to remove that absolute value. This is our first such question. All right. Later we have many. Yeah. All right. So we complete this question, number 4. Okay. All right. Yeah. Next, we need to work on some more questions, but we want to study the structure of separable ODEs. Some special, So what do you mean structure separable ODE? Yeah. So here, let me give you the initial explanation. Later we will see the concrete explanation. Yeah. For the first initial round, the structure. So here, the structure of the equation is important. All right, so given a special equation, in the first view, it's not separable. In the first view, we know the meaning of separable, right? Yeah, but the first view, that equation is not separable. Okay, based on our understanding of the separable meaning, it's not. Nobody can separate it. Two symbols, y and t, but nobody can separate y and t, or yx. Yeah. Nobody can separate. Yeah. But you have a chance to separate them by the special properties of the structure. Yeah. The equation may have some special structures. So you can take advantage of the structures and use the variable substitution. Some appropriate variable substitution. Yeah. After you apply some appropriate variable substitution, then it becomes separable. That's the meaning of this section. Okay? Yeah. So the first view, not separable. Yeah. Don't give up. Okay? Yeah. Try to explore the special structures. If you can really, so here I give you 2 different structures. Yeah. If you happen to find those 2 structures, then you can use the variable substitution to make it separable. All right, yeah. So that's the, the meaning for this one. But before that, I need to review the differential concept. Now, to make you feel more comfortable, let me give you the background of differential concept. Yeah, because we need to use this concept a lot from now on. Yeah, so you have to understand this concept, differential. All right. First, from the history, because this concept gives you some, brief story about the history a little bit. Yeah. The term differential is used non-rigorously in history, non-rigorously, not current. Yeah, current, the definition, everything about differential, very rigorous. But in the early history, it's non-rigorous, right? In calculus, to refer to an infinitesimal. Yeah, because in her early history of calculus, mathematicians use one special concept called this one, infinitesimal concept. Yeah. Its meaning is infinitely small. That concept is not rigorous. Okay, infinitesimal. That concept is not rigorous. So you can see in the current calculus, nobody used that concept, infinitesimal concept, okay? Because it's not rigorous. But in the early history of calculus, so mathematicians, they felt they need to describe this concept, infinitesimal, infinitely small, that concept, to help them understand the calculus, okay? Yeah, so, all right. Infinitesimal change in some varying quantities. Yeah, so then they use that differential concept. Yeah, that concept is based on this infinitesimal concept. So not rigorous at that time. Okay, yeah, all right. Because at that time there was no limit concept. Okay, no limit concept. Then people argue. So what's the meaning of infinitely many small? Right? What's that? Okay, is it a number? Because infinitely small, can you treat that as a number? You cannot, right? How do you? So when people talk about some quantity is infinitely small, that quantity, is that a number? It's because if it's a number, it cannot change. It cannot change. It must be fixed, right? A number must be fixed. Yeah. Then, so many mathematicians reject this concept, so because they felt not rigorous. So they reject it. Yeah. All right. Understand infinitesimal. Yeah. Infinitesimal quantities played a significant role in development of calculus. So early mathematicians, they need this concept to develop calculus. Otherwise, they cannot do anything. If they did not use this concept, they cannot do anything. Okay? So Newton, right? Yeah. Leibniz, those mathematicians, they couldn't do anything without this concept. Yeah. All right. So if x is a variable, then dx denotes an infinitesimal change in the variable x. So that's their early definition of this differential. Yeah, but it's not rigorous. Yeah, because infinitesimal, that concept is not rigorous. Yeah. All right. So then later, several important mathematicians, they work on to make it rigorous. Yeah. They try very hard, so different ways to make the whole theory rigorous. Yeah. Try to replace this infinitesimal concept by other more rigorous concept. For example, limit concept. Limit concept is more rigorous than infinitesimal. Yeah. Limit, yeah, in calculus. All right. Yeah. The use of differentials in this form attracted much criticism. Yeah, so many rejected. Okay, yeah, yeah. The very big problem. Yeah, so then notation remain popular. Yeah, because when people use this concept to solve real-world problems, very effective. Yeah. So Newton, many people, engineers, use that concept to solve real-world problems. Well, very effective. So many application problems can be solved. Okay, nice solutions. Yeah, yeah. But the problem is, the foundation is not solid. Okay, the foundation must be fixed. Yeah. Then the next part, fixing the foundation. Yeah. Yeah. After development of the epsilon delta approach to continuity, limit, and derivatives, in calculus, there is a rigorous definition using the epsilon delta language to define limits, continuity, and derivatives, right? Yeah. Yeah. Although for many people it's not required, that part not required. Okay? Yeah, epsilon delta language. Yeah. For math major students, yeah, it is required. Yeah. For non-math major, usually not required. Okay? Epsilon delta. Yeah. But that's the rigorous way to define limits, continuity, and derivatives. After that, yeah, because when you have the limits concept, continuity concept, and the derivative concept, then you use these concepts then to describe the differential. Then you get a rigorous foundation, because you never need to use that infinitesimal concept. Okay? Yeah. Yeah. So you can use limit. Yeah. So you can use those things. Yeah. All right. So now let's recall the definition of the derivative. Yeah. When we define, so here I show you how to use the limit derivative concept to describe differentials. Yeah. So let's look at the derivative definition. We use limit to define. We use the limit like this. Okay, delta y over delta x. You know the meaning delta y delta x, right? Yeah, the difference. Yeah, difference amount. Yeah, in y values, x values. Yeah, but you take the limit when delta x goes to 0. Yeah, that limit you define as a derivative. Okay? Yeah. Yeah. All right. The limit you use epsilon delta language to define. So what's the limit? Epsilon delta language. Yeah. Here we do not go that far. Okay? Yeah. All right. Yeah. So now then you take with this definition, you take a view. So what's that view? All right, so here, when delta x goes to 0, yeah, imagine, yeah, all right, then delta y, yeah, we know, goes to, when delta x goes to 0, usually delta y also goes to 0, right? Yeah, goes to 0, all right. So here we use so delta y part. Yeah. If you look at the amount, it goes to 0. Yeah. If you look at the value, it goes to 0. Yeah. But here we do not want to use 0 directly, because if you use 0, nothing you can do. When you work on 0, nothing interesting you can do, right? Yeah. So here we do not want to use that 0. Okay. So here we want to use a meaningful representation, differential dy. Okay. We use the dy to represent Yeah. So actually here you can see people do this. They try to get around infinitesimal. Yeah. Infinitesimal. Is this something like infinitesimal? Yeah. Infinitesimal is small, but we want to avoid infinitesimal. All right? We want to avoid infinitesimal. Yeah. Yeah. So here we use a abstract concept differential to represent. Yeah. So that certain amount, yeah, yeah, you know, very small, very close to zero, but it's not zero. Close to zero, but it's not a zero. Yeah. Yeah. That expression, so dy, all right, yeah. And delta x goes to dx, okay, yeah. That representation, all right, yeah, dy dx, that representation, yeah. But they are never zero, okay, yeah, they are never zero. Yeah. There are two symbols, yeah, two concepts, two symbols, yeah. Yeah. But differentials, they approach to zero, approach to zero, yeah. All right, but it's concept, okay, yeah, yeah. It's a not concrete number. It's not a concrete number. It's a notation. Yeah. All right. So yeah, it's very abstract. Yeah. But we need these concepts to help us set up equations. Yeah. Later you will see we need a concept like this help us set up equations. Yeah. All right. Now, so here the relationship between differential and the derivative. dy differential equals dy over dx. That's the derivative. Yeah. So we know the meaning of derivative times dx. Yeah. From the form you can see cancellation, right? Yeah. From the form you can see after cancellation dy equals dy. Yeah. But the meaning is different. Yeah. dy over dx, it has its special meaning, derivative. Yeah. Then times another differential dx. Yeah. Now our interpretation is between two differentials, dy, dx, how to connect these two differentials. Yeah. So we use derivative to connect these two differentials in that formula. Okay? In that formula. All right. Yeah. All right. So you can write y prime times dx. Yeah. Yeah. So in this way, yeah. So you get these two get a differential concept, very important concept. Yeah. So you put it into the picture. So you need to use this concept to help you understand the question. Yeah. So later I will give you an example. Yeah, we need to use the differential concept to set up equation. All right. Yeah. Yeah. It's an instantaneous rate of change. Yeah. Y prime at current instant t. Or current instant x here. We use variable x, not t. Okay. Current variable, current instance. Yeah. X instance, current value instance. Yeah. So it's an instantaneous rate of change. Yeah. Yeah. The understanding. Yeah. All right. Then solve separable ODEs. Yeah. All right. First, the general first order ODE. This is the general first order ODE. Yeah. Very general. That f function, some implicit function, capital F, implicit. Arbitrary, yeah. Could be very complicated. Yeah. That's the implicit function. Yeah. But usually it's hard to solve first order ODE directly from the implicit. Very hard. Yeah. So we like to work on the explicit form. The second one, y prime equals explicit form. Yeah. But the problem is, it is not guaranteed that you can always find an explicit form for a given implicit form, ODE. Yeah. It's not guaranteed. Yeah. Sometimes you can get it, sometimes you cannot. Okay. Are the implicit form and the explicit form equivalent? Yeah. Most of the time, not equivalent. But because most of the time, you cannot find it explicit form. Okay? Yeah. It could be very complicated. Here, I use a simple example. So the first example, explicit. Second form, first example, implicit. Right? Yeah, together. Okay? All these x, y prime, together. The second one, we write y prime representation. Yeah. Because this equation is very easy, simple, so we can write in that way. If you have a complex, very complicated capital F function, then you cannot write explicit form. Yeah. But here, this one, we can write. Yeah. But when you write this one, you need an extra condition. X cannot be 0. In order to make it equivalent, our goal, we want to make these two equivalent. Because in the first equation, x is not allowed to be 0. Right? X to the negative third, this term tells us x is not allowed to be 0 in the first equation. Yeah. So for the second one, if we do not put this parenthesis, then x is allowed to be 0, right? Yeah. If we do not put the extra parenthesis condition, then if we from this equation directly, it is allowed to be 0. Yeah. Then first one does not allow x to be 0. Second one, it allows x to be 0. Then that means not equivalent. Okay. So we have to add extra condition. Yeah. X is not equal to 0. Then we want to make it equivalent. Yeah. That's the meaning. All right. Yeah. So pay attention to the little things. Yeah. Because when we use some algebraic operations, so you change from the first equation to this one quickly, right? You may forget to put some extra condition, x not equal to 0. Okay, that little things you need to be very careful when you solve those equations. Yeah. All right. Can we convert any implicit form to an explicit form? Yeah. The answer is no. Yeah. Most of the time, think about in this one. How can you write y prime in terms of x and y? Okay. Because this y prime inside the sine function. And there is another y prime, right? X. So it's impossible for people to write an explicit representation. Y prime equals some formula of x and y. Okay? Too hard. Yeah. So most of the time people cannot do it. Yeah. All right? Yeah. All right. All right. My remote control. Yeah. Yeah, maybe the battery is weak. Yeah. Battery dead. Battery dead. Yeah. All right. All right. Yeah, I need to change the battery. Yeah, anyway. Yeah. Yeah, all right. So we can only convert relatively easy implicit form to an explicit form. Yeah. All right. Yeah. Yeah. Now we try to solve explicit form. Yeah. If we cannot convert, then you cannot solve it, right? Yeah. All right. Yeah. All right. Explicit form. Yeah. So we consider initial value problem. Yeah. Because most of our application problem, we need to work on initial value problem. Initial value should be given. Yeah. Otherwise, you have some undetermined constant. So you use the initial condition to determine some undetermined constant. Yeah. All right. Strategy. From easier cases to harder cases. Yeah. Yeah. All right. First, the derivative is constant proportional to the function. Well, so let's work on the simplest, easiest form. Y prime equals k times y. Yeah. All right. So it's a separable ODE. Yeah. It matches our decay model, right? Yeah. Matches our, we can say, generalized decay model. Yeah. But here it's also separable ODE. Yeah. So here we can view. Yeah. Also a separable ODE. Yeah. All right. So you can treat it as a special case of the separable case. Yeah, yeah. But so here you can see the separable ODE is a larger class. So compare it with the first case. First is relatively special. Yeah, the separable, yeah, larger than the first type. Yeah. All right. To solve, yeah, if you can separate in the, if you can do this kind of separation, then you apply integration operation so you can solve it. Yeah. All right. Yeah. So the general solution like that. Yeah. All right. Yeah. All right. But that's the, the general description of the separable ODEs. Yeah. Now let's look at our problem number 5. Heating an office building. Our application question. Heating an office building. Yeah. The air conditioning, yeah, heater, in winter, right? So we need to measure the temperature in the office building. Yeah. Yeah. How to model that whole environment. Yeah. So let me give you the question first. Oh, it doesn't. Yeah, I need to use this button. Yeah, first, let's imagine there is office, air conditioning, yeah, office. Yeah. Suppose that in winter, the daytime temperature in a certain office building is 70 degrees Fahrenheit. Okay, yeah. The heating is shut off at 10 p.m. Yeah, all right. And turn on again in 6 a.m. Yeah, all right. On a certain day, the temperature inside the building at 2 a.m. Yeah, so you can measure. Yeah, yeah. 2 a.m. That temperature is 65 degree F. All right. Yeah. The outside temperature is 50 degree F at 10 p.m. Yeah. But that outside temperature also changes. Okay. Yeah. Drop it to 40 degree F by 6 a.m. 40, 50, 40. Okay. Yeah. How to change? We don't know. Okay. The temperature changes from 50 to 40. Yeah. That part, the detailed information not given. So we need to use our imagination, yeah, to make a reasonable assumption. Yeah. All right. What was the temperature inside the building when the heat was turned on at 6 a.m.? Yeah. So here you need to find the temperature function. Here the y function is the temperature of the office. Yeah. So can you find that temperature function, y of t, yeah, in the office? Yeah. Yeah. If you can find that, you can answer this question. Yeah. All right. So let's do analysis, the modeling first. Yeah. So think about, so in this system, the whole system, okay? Yeah. The temperature inside the office, outside office. Yeah, yeah. So what is the physical law you need to use to model this system? The first step, yeah, we need to get that information first before we can solve it. Yeah. So there is a physical law called Newton's law of cooling. Okay? Yeah. Yeah. Newton, yeah, did experiment and it derived this law. Okay? Law of cooling. Yeah. Yeah. So we use Newton's law of cooling to model this problem. Yeah. All right, so what's that law? Yeah, Newton's law. All right. The time rate of change of the temperature T. Time rate, yeah, rate of change, derivative, okay? The change rate, derivative of the temperature, capital T. Yeah, here we use capital T. Temperature, capital T. Little t, that's the time variable. Capital T, the temperature function of a body B. Body, office is the body, okay? Yeah. Yeah. Body B, yeah, is proportional to the difference between capital T and the temperature of the surrounding medium. Surrounding, yeah. Outside temperature, that's surrounding, okay? Yeah. Outside temperature surrounding the office. Yeah. So that temperature also has some impact on the inside office temperature. Yeah. So this is the Newton's law of cooling. Yeah. So we use this physical law to set up equation, yeah, for this problem. Yeah. All right. Yeah. So the formula from this Newton's cooling law, dt d capital T over d little t, yeah, derivative of the temperature, equals constant proportional. Yeah, proportional means we use a constant to multiply some expression, yeah, parenthesis. Yeah. The difference of the temperature, capital T, office temperature, office T, body, yeah. Here are more general because later we need to apply Newton's law of cooling on many other systems. Yeah, so not necessarily an office. Yeah. Later, so we have many other, different objects. We need to apply this Newton's law of cooling. Yeah. All right. So the T, the body temperature minus T sub A, environment temperature, surrounding temperature. Yeah, surrounding temperature. Yeah, but the surrounding temperature. So later we can interpret. So what's the surrounding temperature? Yeah, for different questions. First, you need to distinguish which object is the body, which object is the surrounding environment. Yeah, you need to separate. Yeah. So here, yeah, easy. Yeah, the body, office, okay, surrounding, outside. Yeah. All right. Yeah. All right. So inside, outside. Yeah. But the outside, in Newton's law, the outside temperature T sub A, that term should be a constant. Yeah. Based on the Newton's law, this outside temperature, the surrounding temperature should be a constant. Yeah. But our given condition, the outside temperature is not constant, right? Yeah. At 7 p.m., it's 50 degrees, but at 6 a.m., it's 40 degrees. Yeah, right? Yeah. Drop it to 40. So it's another constant. So that means we cannot apply Newton's law directly, so we need to do something. Yeah. Do some pre-processing, do some work to make it fit Newton's law. Okay? Yeah. So we cannot use 50 because 50 is not good enough. And then we cannot use 40. Yeah, 40 also we feel not good enough. So what do you think? Which number do you think we should use? Not 50, not 40. Is it a better number you feel we should use here? 45, the average of these two numbers. The average, 45. That's the first obvious, way, right? Yeah. So we estimate it, we use average to replace that. Okay? Yeah. At least it's better than 50, it's better than 40, right? Something in the middle. Okay? Not too extreme, right? Not too extreme cases. Something in the middle, yeah? Balanced. At least keep the balanced, right? Yeah. So that's the usual way that people do. Okay? 45. All right. Now we have a concrete equation. This is the concrete equation. Okay? And it's separable, right? It's a separable ODE, and we can solve it. Yeah. The separable ODE, everyone, you can solve it easily, right? Yeah. Yeah. All right. So let's solve it. Yeah. We have initial condition T of 0 equals 70. Yeah. T of 4, yeah. T of 0, 70. So we need to set the 0 time. Okay? So the 0 time, we use 10 p.m. That's the T equals 0 time. Okay? 10 p.m. Yeah. As our reference point. Yeah. So we calculate our time. Yeah. We set 10 p.m. as our starting point. Okay? All right. Then, yeah, because 10 p.m. Yeah, at 2 p.m. If 10 p.m. is 0, 2 p.m. after 4 hours, right? Yeah. If you count from 10, then after 4 hours you get 2 p.m. So this means, yeah, at this point, T equals 4. Yeah. So that's why T of 4, the office temperature. T of 4, that's office temperature. Okay? Yeah. Office temperature, yeah, is 65. Yeah. Right? Yeah. So that's the given information. The question, you need to find the temperature at 6 a.m. So what's the corresponding T? 6 a.m. Yeah. You count from 10 p.m. From 10 p.m. after how many hours you get 6 a.m. Okay? Starting from 10 p.m. Then after how many hours you get 6 a.m. 8, right? 8. Yeah. 2 hours you get midnight, right? 12 a.m. Then another 6 hours, 2 plus 6, you get T equals 8. Okay? Yeah. So the question is, you need to find T, capital T of 8. Capital T of 8. Okay? Yeah? So, all right. Next, we need to solve it. No, sorry. Yeah. All right. Yeah. So here, yeah, so we have a few minutes. Yeah, let me work on this. Okay. Although it's not hard. Yeah. So the remaining time, let me just complete the solution together with you. Okay. All right. So now, this is the whole question. Okay. Yeah. But our goal, we need to find T of 8 equals what? That's our goal. Okay, all right. Separable, yeah, so we have the experience. So we write in the separable form all the T terms at the left-hand side capital T terms, and all the little t terms at the right-hand side. How about that? Okay? Yeah. All right, the first step. Yeah. Then we need to calculate the integral, right? Calculate the integral. Okay? Yeah. But the right-hand side is easy, right? Right-hand side, k times t plus some constant c. Easy. Yeah. But the left-hand side, we need to do some small transformation. Yeah. Because this denominator form, minus 45, can we write it as d of t minus 45? Because we want to make it the same. Denominator and the part inside d, the same. And the d of 45, that's 0. So basically we minus 0, so nothing changes. Okay? Nothing changes. So that's why we make up. Yeah. So we minus 45, because when we make this d parenthesis, inside parenthesis, the same as the denominator, then we can apply that logarithm formula, natural log, right? Natural log, but don't forget absolute value. Capital T minus 45. Yeah. So then we can write capital T minus 45 equals kt plus c. Okay. Yeah. Now the question. Yeah. Now the question. We want to get rid of the absolute value. Absolute value. Can you see capital T is greater than 45 or less than 45? Capital T. That's the temperature inside the office, right? Inside office should be greater than outside temperature, right? 45 is outside temperature, between 40 and 50, outside temperature. Inside temperature at least higher than outside temperature, right? Yeah. So we can reasonably, assume capital T greater than 45. So we remove the absolute value equals e to the capital C times e to the kt. Yeah. But e to this capital C, we plug in the initial condition t of 0 equals 70. Plug in. So we want to figure out that capital C term. Yeah. So 70 minus 45 equals e to the c. Okay? E to the c equals 25, right? E to the c. We can replace e to the c by 25. Okay? All right. So then, from these two, can we write capital T equals 45 plus 25 e to the kt? How about that? Yeah. So we write that formula. But little k is unknown, right? Little k is unknown. Yeah. To determine little k, we need t of 4 equals 65, right? Little k. Yeah, we have another condition we can use. Okay, t of 4, that means 65 equals 45 plus 25 times e to the 4k. How about that? E to the 4k. Okay, all right. Yeah. Then, based on these two equations, can you find t of 8? Because you can find a little k if you want, okay? If you want to find a little k, you can find it. Yeah. From the second equation, you can find little k. Yeah. Then you plug in the first one, you have the k. Then you plug in t equals 8, you can find its value. Right? Yeah. Yeah. All right? Yeah. So here I the remaining part, just calculation. Okay, you can use calculator to do the calculation. Okay, you can use the Wolfram Alpha to calculate it. Okay, yeah, online calculator, Wolfram Alpha, yeah, very powerful. Yeah, so usually in this situation I use Wolfram Alpha to do the calculation. Okay, yeah. All right, so that's it. So we complete problem number 5. Yeah. So next time we will complete the remaining. There is number 6, and after number 6 we have structure discussion. Yeah. I need to give you 2 special structures for separable ODEs. Yeah. All right, so that's it.